record. Well, hello everyone. This place is very cluttered and I'm trying to navigate in between all these cables and flowers. I don't need this flower. Now, can you tell me how many of you attended the first course on AI? Okay, so the rest of you were not participating in the first course, which was the video course. No. You all did. Okay, excellent. So I'm gonna skip the introductions. I'm not gonna introduce myself again. This is the first 3 slides, have the University of Warsaw logo because I designed the slides beforehand and I really don't have the patience to change the slides now again. So only the first 3 slides will have the logo. That's all about me. My name is Peter. I work for the University of Oxford. I'm only here teaching for this course, for the winter course. I'm here for a week and I think you're lucky. We don't actually get the quality of chairs and the quality of these buildings that you have here. Warsaw, it's a very new city and I would compare it to Zurich. I wasn't expecting Warsaw to be so developed. Many years ago, they used to say that Warsaw, it's on equivalent level to Sofia or Skopje. And now I would compare it to Zurich or, I don't know, some very advanced city. So that's me. In this course, we're going to be talking about post-quantum security. If you think about the new technologies that they are emerging, there are very few technologies that would change the world in the future. Artificial intelligence is one of those. We covered that in the first slide. We're going to be talking about agentic AI in some of the future courses. In this course, we're specifically going to talk about post-quantum security. Now, how many of you can tell me anything about the current standards about post-quantum security? And I'm not doing this to test you. I know this is a faculty of law and administration. I'm not expecting you to know much, but I need to know that in order for me to adjust my level of teaching. So if I ask you to tell me what are the 4 standards for post-quantum security, how many of you can tell me those standards? Nobody. If I ask you, for example, who is the body that governs post-quantum security? It's NIST, National Institute for Standards and Technology. So it's not the institute in the European Union, it's an institute in the United States. Most of the algorithms that we use, RSA, ecliptic curve, most of our current cryptography, it's developed in the United States. They govern and they standardize those algorithms. So the post-quantum security, post-quantum cryptography has been undergoing 10 years process of standardization. NIST, the National Institute for Standards and Technology, has done that for us. We had a very strong objection from the European Union, from the United Kingdom, from China, from various different countries who were saying, we don't want the US to govern us. We want to have our own processes. Yeah, good luck to you. That took 10 years and European Union didn't take action at the time. So if you want to select the best post-quantum cryptography algorithms specifically for the European Union, from today you need to have a 10-year process. And if you repeat that whole process, probably you're going to end up with exactly the same algorithms, which they won't really be the same because in 10 years the cryptography will change. But if the European Union and the US in parallel develop the same process, it would have been the same algorithms. Now what I'm going to show you, if I have time in this video, that the algorithms that the US adopted, they're actually developed in Europe. There's a limited number of cryptographers that understand post-quantum cryptography. I will show you with demonstration how difficult it is, and it might take you a lifetime, and you might never understand just one single algorithm. So cryptography, it's a very technical and very mathematical subject. In terms of law and administration, you don't really need to understand the ins and outs of cryptography. Actually, I'm going to go a little bit further and I'm here on camera, so I'm confident that it's correct what I'm saying and I'm going to support that with evidence. There's around 5 or 6 people and those names keep repeating in every algorithm that is accepted for standardization because the world has a capacity and there's not more than 5 or 10 people that can develop such algorithms. I'm going to give you a different example in terms of hacking. I work in security. I'm not a cryptographer. Cryptography is part of security. I'm not specifically a cryptographer. And my area of specialization is attack and penetration. The biggest conference on hacking is DEF CON in Las Vegas. It's like the mecca for us. How many, there's like between 30 and 50,000 participants. How many of those do you think are really good hackers? Number? Out of 50,000 participants.
1-2%.
It's between 10 and 30 people, individuals. So this room, this room is basically what you're gonna get in terms of good developers with good hackers out of the 50,000 people. So it's technical skill set that not many people can develop. Why do you need to understand post-quantum cryptography? Hold on, can you see the slides? You can't really see the slides. It's difficult because I can't really navigate. So if you need me to move, let me know and I'll move. Why do you need to understand post-quantum cryptography? Because of the time travel attack. Now, I do get journalists trying to interview me, and I do get many people asking me questions, and the biggest fear is, can Russia develop a quantum computer, hack Poland, European Union, US? And if you accept that as a postulate, your position, imagine the security as a chessboard. If you accept that as a postulate, you're accepting the wrong postulates. So you're positioning your defenses in the incorrect place, and you're not securing the parameters that you really need to secure. Russia is not developing a quantum computer. Russia does not have the capacity, the money to develop a quantum computer. We're talking about trillions. And if you're thinking, who is going to develop a quantum computer? Well, we already have a list of quantum computers. Okay. List of quantum processors. This is how easy it is for you to find the information if you know what you're looking for. This is the list of quantum processors. So briefly, I'm just going to scan through it. Pay attention to the manufacturer. So in this column here. Because if you think that Russia will develop the next quantum computer, in the next few seconds you're going to change your opinion. So none of these manufacturers is based in Russia. Atom computing, Google. You see how many chips are developed by Google. Willow is the newest, well, one of the newest chips from Google, and I'm going to show you what it's capable of. It's much faster than any of the best supercomputers. IBM, so you look at the list of how many quantum chips processor has IBM. Where is IBM? It's not in Russia. And I'm going to scroll down this list. Intel, these many, Oxford Quantum Circuits. None of those organizations is based in Russia. So from looking at this list, yeah?
Should we see this list actually, or?
I showed you how to get the list. You type in Google.
Oh, okay.
Yeah, so this list is publicly available.
Okay.
So list of quantum processors, and this list will show up. Now, why am I emphasizing this strongly? Because every time I get a journalist who would be young, enthusiastic, naive, and they're very afraid from Russia. Russia is Baba Yaga, scaring us all. In terms of hacking, Russians, they don't really need a quantum computer to hack Poland or other countries. They just need a very cheap Dell device, probably cheaper than what you use. So hacking is a skill. You're exploiting vulnerabilities, and to develop something that is going to take 10, 20, or 30 years before you can use it, it's not in the national interest of a country at war. So who is going to develop the quantum computer? It's going to be one of the countries that they are investing money, they're publicly investing money, not secretively. You cannot hide trillions. You can hide few millions maybe, but not trillions. And that's what it takes to build a quantum computer. So who is pumping the most money into quantum computer? Just a guess, tell me a name.
US.
Okay, on a national level or on an organizational level?
Go.
Wrong.
Oh no. on organizational level, US and China on national level,
Yes.
right?
Correct. So China has been pumping 5 times more money to quantum computing than the United States, 15 times more money from the government budget than the United Kingdom. Those are the 3 countries that they are developing quantum computers. We have quantum computers in London in various different cities, but China is putting 15 times more money from the government budget into a quantum computer. US, most of these chips are US companies, but that's not from the US government budget. That's from a company. IBM is a company. Actually, the budget of IBM is probably bigger than the budget of Poland and most of the Eastern Europe. So it's, as an organization, you can consider it bigger than most countries. But on a level of government, China. So if you're now, when you're positioning your chessboard, who can attack you with a quantum computer? Clearly, the countries that will have a capability to attack you. Those are not only China, US and the United Kingdom. It's difficult and it's very wrong to position China as the enemy. We are not at war with China. So the hacking group might come from the United States. Who is to say that Donald Trump won't lose his mind tomorrow and just for fun break the encryption of Poland? That's more likely to happen than China. China is actually a very reliable and steady trading partner. Now, with that in mind, I can see that person over there picking on. Do you have a question, sir? Or?
Yeah, I mean, let's go back to the World War II and you know who pressed the button for Hiroshima and Nagasaki.
Exactly. So now changing that narrative into something else. Government, it's unlikely to attack another government unless there is a war. So who is going to use this kind of technology? Hacking groups. What we call APT, Advanced Persistent Threats. Quite often they are nation funded. And in some of the other courses, this course would be too short. Actually, anybody knows what time do we need to finish? Because I don't even know. But we do have time. Let me know when you look into the timetable, what time do we actually have to finish, so I can change the pace of the PowerPoint slides. I think it's like 90 minutes, then lunch. 12 o'clock. Okay, so we have another hour. So what happened with the transformer architecture? With ChatGPT, everybody has a generative AI on your phone now. First we had OpenAI, but actually OpenAI stole it from Google. Google developers developed the transformer architecture in a paper called Attention is All You Need. Then the next year OpenAI took over that, and OpenAI has invested a lot of money into building this technology. That's why we say it's an AI bubble, because the share value, the share price of OpenAI, it's really pumped up. The share price of Nvidia, it's really pumped up. The share price of these very few organizations that we think are capable of delivering that service because they paid money. Then DeepSeek came in and stole the algorithm. Well, stole it. It's not actually stolen. Legally, there's nothing you can do against them. That means that they haven't stolen it. If they have actually stolen it, you could have sued them and taken action against them, like they're doing against TikTok, which that's also a controversial topic. There's no legal case against DeepSeek. Basically, they have extracted the knowledge from this model and they have developed a very capable model for a fraction of the cost. Now, what does that tell you? OpenAI is hugely overvalued because a different company can provide the same service and it didn't cost them billions to build that. So when you have quantum computer, going this back to the quantum computer, when you have a quantum computer, China develops it, US develops it, UK develops it. How long do you think it's going to take for countries like Russia or for hacking groups, Iran maybe, those organizations that they are beyond your reach, that you cannot go there and arrest them, North Korea? How long do you think it's going to take for one of those organizations to clone that quantum computer and develop a calculator that is going to break our current cryptography? That is where the fear is. It's not the fear that China will hack us, although they would probably develop the capability first, China or US or the UK. Those are the 3 countries that they have the most potential. Once that technology has been developed, everybody in the world would be able to recreate it and hack us. So what is the fear for you today is the time travel attack, what we call the data that you're producing today. If it's still going to have value in 5, 10, 15 years time, many organizations, many hacking groups are currently storing it. So if you have what kind of data does produce value, it's not your personal chat messages between your girlfriend or a boyfriend, probably it's not even going to be your girlfriend or boyfriend in 15 years time. Average relationships, marriage would last around 7 years. So what data has value in 5, 10, 15 years time? Bonds, share prices, banking transactions, national secrets, things that you don't want people to know. Currently, we are transmitting that information publicly via the network because it has RSA encryption. RSA is a cryptographic algorithm that the current computer would take more than the age of the universe to break. Quantum computer can break it within a few seconds. So now we are transmitting this data between the US, the UK, Germany, France, national secrets, confidential information, banks, financial data, and that data is only maybe a fraction, maybe 1% of the total volume, probably a lot less than 1% because there's a lot of social media, lots of videos, lots of YouTube channels being transmitted. So that 1% needs to be secured today because hacking groups are storing it in 5, 10, 15 years time. They're going to be able to open the files, read them, because currently they have a string of numbers, zeros, numbers, hashes. That's how it looks today. You cannot break it. With a quantum computer, you can. So if it's going to have value, that is the time travel attack. It means that you can go back in time and break the files that they're stored today. Now, how many countries do you think are protecting their national secrets and transactions that are being sent over the internet? How many? Do you think Poland or the European Union is encrypting with post-quantum cryptography? Not you, sir. I know you know the answer. Can somebody else tell me? Is Poland, for example, or European Union encrypting currently the top secrets that you're transmitting from Poland to Berlin? No, you're not. And if you're going to encrypt it, what algorithm are you going to use? Poland does not have algorithm. European Union does not have an algorithm. United Kingdom does not have algorithm. The only approved algorithms are the NIST algorithms from the United States. Now, if you're, as I said, if you're going to repeat that process, China, by the way, is repeating the process. China said, we're not going to trust the Americans, we're going to do our own process, we're going to have 10 years, we're going to build our own algorithms, we'll do that on our own. But they are capable of doing it. They have the capabilities to do it. I really doubt that the individual country in the European Union has the capability to secure on the level that is required. Now, if we Google this and say NIST post-quantum cryptography, for this, no. For this, I'm looking for an overview. This was round 1, as you can. Oh, well, you're not actually seeing my screen because I'm on PowerPoint. Yes, so I was talking about the other thing that's why you were asking me. Yes, I get it. Okay, so this is round 1 for the NIST selection of the post-quantum cryptography algorithms. This is the whole list. You see how many there are? Currently we have 3 or 4. So this was the first round. So the first round, and then the second round, and the third round. How do you think they selected these algorithms? What was the basis for the selection? They called companies like Microsoft, and they asked them, can you do it? So I have this very secure algorithm. This is going to provide the best post-quantum cryptography. Can you implement this into your technology stack? And if no, it's out. Then we need a different algorithm that can be implemented. So they went this through rounds and rounds and rounds and rounds until they actually develop algorithms that can be implemented in Google, in Microsoft, in OpenAI, that they can be implemented using hybrid cryptography. That means that you have that small part of your data set, that's the 1%, which you need to encrypt. You have that encrypted, but the rest of it is not encrypted with post-quantum cryptography. Why? Because it's expensive. So there's a 99% of your data that has no value. Why would you encrypt all that, pay the money today, put that burden on the government, on the organizations, when it's not necessary? It's not secret. Actually, even if you publish it online, nobody cares. Many of you are PhD students. When I was a PhD student, I used to carry my PhD thesis in one of those backpacks. For 5 years, I put the backpack everywhere. I went on the bus, in the toilet, in the restaurant, everywhere. When I actually passed the Viva, published it on the internet, and I put it in what it used to be called Google Plus, the alternative for Facebook. And I wanted to see how many people would read it and who is going to read it, because it had that tracing. So first week passes, 0 views. First month passes, 0 views. First year passes, 0 views. Nobody actually cared about my PhD thesis. So I've been carrying this document as a top secret in my backpack for 5 years. When I published it online, nobody actually even clicked on the link. Nobody was interested in that topic. So 99% of the data that you store and you consider it very valuable, it's only valuable to you. It does not have a commercial value. It does not have secrets, nothing like that. So this is the list. Now, since I've been talking about processors and scrolling on, looking at this screen, not looking at that screen, this is the actual list that I was talking about. What is that beep beep beep?
It just does that.
Okay, so-
Security system.
Sorry?
The security system.
Security system. So this is the list of quantum. I really need to do this. List of quantum processors and manufacturer. If you look at this here, manufacturer, you see Google, IBM, Intel. So you see that. So for the rest of this presentation, I'm not going to use the full screen mode because I'm going to forget. I'm looking here and I'm going to forget. I'm going to forget to exit every time I use the Google. So I'm not gonna, I hope this is not gonna frustrate you, but I'm gonna use this mode. Because this, when I flip screens, it's gonna stay like this. What I could do, I could minimize this here. There you are. So, that's a very long explanation of why do you need post-quantum cryptography. Now I'm gonna move to the second slide. Here, we have an image. Which if unless I go into full screen mode, I cannot zoom in, so I have to go full screen. So you see, when you're in full screen mode, you can zoom in. Beep, beep, beep. It's good that if somebody has obsessive compulsive, it will go crazy with that beep, beep, beep. So you see, this is a table. It might be a little bit confusing, so I'm gonna look here. This was developed last year. So what data is at risk in 2025? That. Insurance, public sector, banking. Because of the time travel attack. That data was at risk as of last year. It's not going to be at risk when we have a quantum computer. But what data is at risk between 25 and 30? What data do you have, let's say, 5 years' time in order to protect it without significant compromise? And that's the green one. Life sciences, most of the research papers are published in open access. Actually, we do have something called, I can't go to Google because I'm going to show you DORA agreement, which means that we have to encourage the universities to publish our work in open access. Most of my papers, if you go to Google Scholar, are all open access. Oxford pays around £3,000 for each one to be published in open access. So it's not that life sciences does not have any secrets, but that's very minimal. Yeah.
So does the time travel attacks probability increase with the increase of data shelf life and systems life cycle?
The longer the data life cycle, the longer that data is valid, the longer that data has value, financial, secretive, that's the risk is bigger. So if you're going to have a quantum computer, I have a timeline here of when you're going to have a quantum computer based on the companies that they are developing quantum computers. So the reports from them, not the reports from some people. If you ask somebody who works in physics, they would say that we're never going to have a quantum computer because the physicists are very skeptical. Yeah.
And do you work with any of these sectors specifically, or with private sectors in the US or NIST on?
I work in cybersecurity young lady and I work with all of those sectors. So I work on security in banking, I work security in public sector, I work on security in insurance, but I work in cybersecurity. I don't work in banking, I don't work in insurance. So, more questions?
No, I'll have follow-ups though.
So, those two, did somebody raise a hand? Yes?
I'm just, you mentioned the physicists are really skeptical.
Yes.
Why are they so skeptical?
Because quantum physics, it's a very difficult subject. Einstein called it spooky action in the distance. Even Einstein couldn't figure it out. So you take, how is the quantum computing working? It's with qubits. Actually, when we used to teach physics many years ago, we used to start with the theory of relativity. Now we start with qubits. If you go to university and you enroll on a physics degree in Oxford, the very first lesson, this is, even Professor Brian Cox agrees about this, you start with qubits because it contradicts anything that you're gonna learn. So you learn how the universe is expanding, how yada yada yada, theory of relativity, everything makes sense until you get to the lesson about quantum mechanics. Then everything changes. And the qubits would contradict anything that you know about physics. So I'll give you an example. In physics, you can never travel faster than the speed of light. If you travel faster than the speed of light, that means that you're time traveling. Because by the time you go, let's say, from here to the other edge of the universe and then back, this would change. The time would have passed for everybody else except for you. That's what physics teaches you. Now, with qubits, it's different. If you take two particles, this is what Einstein called the spooky action in the distance. We took two particles and we entangled them. Basically, if you put them in, you observe them in the state, they take the same properties. They're connected. Then you take one particle in Europe, the second particle in South Africa. If you change anything to this qubit, that qubit, they had like really smart watches that they were counting every second, at a fraction of the time. That particle in South Africa changes instantly, faster than the speed of light. So how does it do that? This is what confuses physics. There's an explanation which doesn't make sense even to me. So they're saying it's traveling, it's changing, but it's not actually traveling because it's the same qubits that they're connected. So although this qubit is here and the other qubit is in South Africa or the other edge of the universe, it didn't actually travel because they were connected. How? It's not here, it's in South Africa, so it has to travel. So that is why physicists are very skeptical, because if you start getting into it, it gets very confusing. Now, if you look at this from a computer science perspective, and it changes completely. As an engineer, I remember going to a coffee room and I had two friends that are physicists, and the door unscrewed a little bit. So they spent loads of time talking about how to best elevate the door in order to screw the thing back, but they couldn't do anything. And for an engineer, for me, I just took a roll of paper from the kitchen roll, I lifted the table and I screwed that and it worked. That's what an engineer does. We don't need to understand the physics in order to screw the bolt. But for physicists, that is important. They want to know why the qubits, and they say we're never going to understand. Correct. I don't try to understand how the qubits operate, but I know that in a quantum computer, if you send something from here to South Africa, and if somebody in between tries to intercept it, it will change the properties. That's the only thing I need to know, because from a security perspective means that it's unbreachable. I'm gonna know that somebody has observed that qubit, that particle. So the man in the middle attack is when you have two devices and there's a man in the middle who reads, this is Alice and Bob, and then there's I usually explain this with romantic things, that you have Alice and Bob sending a secret message and there's Ellie in between that spies on their messages. So that's the man in the middle, if you want to put it in a very simple term explanation in 5 seconds. So if that happened with a quantum computer, Alice and Bob would know, because instantly it would change the qubit properties. Now, that's a long explanation why physicists are very skeptical, but from a security perspective, what we're trying to build, it's a very simple calculator. From what quantum mechanics can do, we're just basically building a quantum calculator, and that quantum calculator would be able to break the current encryption methods. That's all that we need to do. For us, that's enough. We don't need to know what else quantum mechanics can do. And how far are we into building that? 5, 10 to 15 years time. We're gonna have that in 15 years time. We're gonna be able to break the current encryption in 5, 10 to 15 years time. And that means that anything that you have of value today that is still going to be valued in 5, 10, 15 years time needs to be encrypted today. Not in 5, 10, 15 years time. Then it's too late because
Just one question. So you said that realistically there needs to be a lot of correction in the system when it works. So do you think that that is also achievable in the next 10 to 15 years when this technology is full-fledgedly developed, and what do you think of the
What
scale?
corrections specifically do you mean? Because I mentioned many corrections that they need to happen.
So for the qubits that are used, you said that there is a lot of correction that needs to be done on a...
The quantum correction error.
Yeah.
Yeah. Okay, let me exit from full screen mode. Otherwise I can be talking and there won't be anything behind. So let me Google Willow. Because I do work with loads of, I teach on the professional master's program. Some of my students are really much higher than me in terms of money. So they work for MI5, MI6, they're top spies, or they work for Google, they work for Microsoft. They earn 10 times my salary. So they challenge me all the time with questions like that. And I'm used to showing them a demonstration as opposed to my opinion. This is very contrary to how academics teach. Academics teach, I'm the best, I know all the answers, I'm gonna tell you the answers straight away. But my students, they don't like that. My students are like, well, I don't trust you. I mean, I earn 10 times more than you, so how do you know this and I don't know that? So I tend to show them. So it's not me saying it. So meet Willow. This is actually not a new chip. This is from 2024. Look at the date here. So this is from 2024 when we started really being concerned about quantum computers after this. So what did the Willow do? Willow is one of the chips from Google. So if you look at the list of processors here, let's find Willow. Google Willow. There you are. So it's on the list of processors and we're looking at Google Willow. We're only going to look at 2 paragraphs here. We're not going to look at anything else. We're going to look at those 2 paragraphs. So the first paragraph is what answers your questions. Most people will focus on the second paragraph, not on the first one, but actually the first one is a lot more concerning. So the second paragraph that people read, let's read it together. Willow performed a standard benchmark computation in under 5 minutes that would take one of the world's fastest supercomputers. You know what a supercomputer is, not a normal computer. It's a computer that has loads of GPUs and CPUs connected together, and we find a way how they could work together without, and we create a supercomputer that can process. So we have one in Cambridge called Dawn, that's AI supercomputer. We have one in Bristol, we have one in Edinburgh, we have loads of supercomputers. But it's not a computer, it's like a supercomputer. So Willow, in under 5 minutes, they performed something that would take the fastest supercomputer 10 septillion years. And that is the number that exceeds the age of the universe. So if you take one of the fastest supercomputer in the world, what Willow did in 5 minutes, it performed a computation that would take that supercomputer 10 septillion years. So basically never, it's not gonna happen. You can't even power a computer for that long, you know. I mean, we're all gonna be dead, so why do you care? But the first part here, it's more important for me. What the Willow did is, currently we have a problem with connecting enough qubits and maintaining them for long enough in order to do anything useful. I usually compare this with spinning plates. So if you don't know what spinning plates, I'm gonna find an image of spinning plates. Imagine a qubit like a spinning plate. Now you need to have, to break RSA, you need to have around 4,000 qubits working together. That means one spinning plate, one qubit. You need to have 4 spinning plates in the same time, but not in line as they are. It's going to be one on top of each other. So you have one spinning plate, you need to put another stick in another spinning plate. That's how difficult it is. You need to have 4,000 spinning plates. At each point in time, one of those plates could collapse. So that's how difficult it is to maintain the quantum qubits, and that's why the physicists are so skeptical that we're ever going to have a quantum computer, because you cannot sustain them. For them to be productive, you need 4,000 of them working together. And you have physical and logical qubits. So those 4,000 would need to have support qubits, many, many more, hundreds of thousands of the different type of qubits. Now what the Willow did here, it's something that nobody actually paid attention. Everybody looked at the second one. They said we can fix the quantum correction error. The more qubits we add, the easier it's going to be to control them. So that's what Google is doing. And Google as an organization is not known to be lying. So there are few individuals like Elon Musk that would say something crazy that I will go to the moon, and people would think, well, hold on, this guy will actually go to the moon because he's proven that he will deliver, regardless of what you think about him. He has a very eccentric lifestyle. Yesterday in the news media, he has a son who is he has a daughter who is a transgender, but actually her original sex is male. So yesterday in the news media, he said she's not transgender. He's my mentally disabled son, and everybody's going crazy about that. That's what he posted on Twitter. So regardless of what you think about Google, if they say that they're going to do something, usually means that they are very confident that they will do it, and they're saying that they're going to fix the quantum correction error. So it's the answer to your question. I hope you. And if you want to know more about that, you're gonna read this. You can read this below. thing. So going back to full screen, if you see me talking about something and you see the wrong screen, let me know and I'll fix it, because I can't turn around back. Harvest now, decrypt later. This is the type of attack that we discussed. It goes by many names. I call it time travel attack. That's how it used to be called. That's how I'm used to calling it now. They changed the name to harvest now, decrypt later. You get the data now, you decrypt it later. So going this back into the concept of Russia, if I was advising Putin or Russia what to do today, I would say store the data. Store the data. As soon as we have a quantum computer, I mean, you're going to be able to recreate and reverse engineer that within months, because there's usually some underlying technology that would enable China, US or UK to develop it. What led to RSA being developed in the same time by UK and US? It was the underlying mathematical formulas that they were developed 2 years before that. So something will trigger, some solution will be resolved, like the quantum correction error, and then China will develop a quantum computer, US, and then you can really easily reverse engineer that. So if I was advising Putin what to do today, I would say store this data. When you send your boats around the North Sea and you're looking at those cables, plug into one of those cables, start storing that data. You're going to be able to decrypt it in the future. That would be my advice. That's where countries and nations need to position their security points. Russia is not going to develop a quantum computer. They are not actually developing quantum computer. Going to the next slide. Here we have Slido, and you need to scan this barcode. Or if you cannot scan the barcode, just type slido.com and type that number 328-2539. I do have many questions. We only have half an hour left. We're gonna go through the slides at a faster speed now. This, what we covered, is probably the most important thing that you need to know about quantum security. So in summary, while you're connecting to Slido, in summary, what is the biggest risk of quantum computing? The time travel attack. So that is what you need to be worried about, that some data would be decrypted in the future. Who is going to build the first quantum computer? China, US, or UK? Who is going to abuse that quantum computer? It's a hacking group. Young lady, are you trying to log in and you can't?
No, I think he needs to open the question.
Yes. And then I need to exit from here. So which factor creates legal exposure? Where is Slido? Post-quantum security. There you are. So I guess you have used this before, and I'm gonna keep this as an active pool, and then I'm gonna go and run to the other slides. Please answer this question, and we're gonna look at the answers as we go along. So which factors create legal exposure? Now, take your time with that. I'm gonna go to the next slide. Quantum threat model for law and business. Quantum capable adversaries, what would they do? How do you break RSA? We said that RSA, the current cryptographic systems, can be broken. How can you break them? Well, there's somebody professor called Peter Shor. He works in MIT, Massachusetts Institute of Technology, and he developed an algorithm for factoring numbers. So according to that, and I do have a link to his profile. I'm going to show you the paper if there is sufficient time. Clearly, you cannot cover everything in a single session, but remember that name, Peter Shor. Shor algorithm, it's named after the creator. Actually, this is very common in cryptography. You have RSA. It stands for the first letter of the three people that created the algorithm. So Riverest, Sharman. So this is, or BB84. When we talk about post-quantum, this is actually extremely important. I have to cover this because even if we end the session today, this is probably the last thing that you need to remember. When we talk about post-quantum cryptography, it's not the same as quantum cryptography. Post-quantum does not mean better, does not mean stronger, it means weaker. Post-quantum cryptography is based on mathematics. Quantum cryptography is based on physics. We can only implement post-quantum cryptography, which is based on mathematics. We cannot implement quantum cryptography. So let's look at BB84. And again, this is extremely easy to find if you know what you're looking for. BB84 is going to be the only search thing that will show up. So this is the algorithm, BB84. And, oh, now I'm getting it on Polish. How am I getting it on Polish? I'm using a VPN. I'm in the United Kingdom. But anyways, I don't understand Polish. So those are the two people that created the BB84. So the two surnames and the year was 84. Since 1984, we know that you can have quantum cryptography. We don't know how to implement it. When you think, why do we need the NIST algorithms? Why we cannot develop our own? We don't know how to implement these algorithms. It's really, really difficult. So if you want to lose your entire life thinking about how to implement, this is a good way. You know, you can work on BB84. You're probably going to spend your entire life. You're not going to find a way how to implement this algorithm. Many people have tried. You're not going to be the first one. But this is completely different than the post-quantum cryptography. Harvest now, decrypt later. Okay, I'm very good. You understood that. So I'm going to shift to the second question, which is going to come up. This is a word cloud. In one word, type what data would cause the greatest legal damage if decrypted in 10-15 years time. What type of data? This is just one word. What type of data? Now I'm going to go through the slides with a little bit quicker pace because we only have like half an hour left. So we explained Shor. I'm looking at this note here, and Shor is extremely important. This is the next question that we have. Here we have links to the two professors. I'm going to be talking about these two people when you're answering that question. Peter Shor and Love Grover. Actually, if I put in maximum, those are links. So now it's going to open the link. When I click on it, it should open the link, but you cannot see it. And Love Grover. Okay, so I have opened those two links, and now I'm exiting the mode. This is Professor Peter Shor. Actually, he's still alive, and he still teaches. If you are in the US or here in Poland, he was on the Yugoslavian Olympiad, so he won mathematics competition. If you do have a chance to attend one of his lectures, it could be an opportunity of a lifetime. I went to MIT, I was a Fulbright fellow at MIT, I went as a PhD student and as a postdoctor, and I didn't go, and that's one of my biggest regrets. Now, this Love Grover, it's a second person. Now, what I'm gonna do here, I'm gonna type his name just so you have an image of a person. That's Love Grover. He's not a professor. I call him professor, but he's not a professor. He actually didn't work in academia. And he created the second most important algorithm for breaking current cryptographic system. He's from India. He worked in industry. He made loads of money. For a very short period of time, he was a visiting associate professor. I'm a visiting professor here. Does not mean that I have an association with University of Warsaw. So he was the same. He never had an academic career, and he wrote one of the most important algorithms for breaking current encryption. He was not even an academic. He had that was his hobby. He had a real job making money. And Indians are actually very popular for that. So there's a movie called, I don't remember the name, but Rajamushinai is the Indian mathematician who developed the formulas for detecting dark matter. He didn't have any formal education. He didn't go to school. He worked on a farm. He wrote some mathematical formulas and got invited into Cambridge. He didn't even know how to do the proofs. So, like when you write, you have to write proofs. He didn't know that you need to write proofs. So those formulas, they just kept coming into his mind. And it's not a coincidence. There's something over there what makes some individuals really good at mathematics. So Love Grover, it's the second person. There are two people that they have proven to us that you can break current encryption. That is not that safe as we think it is. Here I do have loads of resources that you can read in your own free time. First is on the introduction of quantum computing and cybersecurity. So how does quantum computing affect cybersecurity? There's a whole list of papers here. I can open one of those here. This is the basics of quantum mechanics and quantum computing. Remember the basics. So I can open just one. I can open this one, University of Waterloo. I can open this one. You might lose the willingness to live in the next few seconds. So this is the theory of quantum information. It's a book, but the author published it as a preprint. That's what a preprint means, that it's before it actually gets the official. Now, if I open this in Google, it does something much better than this. It actually gives you the PDF. Safari doesn't do that for some reason. So you see the number of pages here. 598. It's 2 pages short of 600 pages. Let's look at some of the pages here. This kind of formulas are, so you have 600 pages of this. This kind of language is only understood by a few people. I do have a friend, she graduated her PhD from Cambridge. She's very smart. She knows how to implement this, but she doesn't understand it. So you have 600 pages of formula like this. I mean, if I could recruit one of you to scroll through this, I'm sure that you're going to get depressed just from looking at this. So she found one formula and she said, okay, I can understand this one formula. It's been 10 years. Every year on Facebook she posts, I still don't get it. So now she left academia, she found a real job, she got married, she has children, and every year she posts on social media, she says, I know how to implement this, I know how to code it, I don't understand it. 10 years, she doesn't understand one of those formulas. It's very difficult to know this. It's not that easy. And I'm going to show you, if we have time, the actual algorithms that they're developed for post-quantum cryptography. Is the same group of people that they developed them. So this is on the basics of quantum mechanics, because the young lady over there asked me why we cannot implement it. That's the answer. It's really difficult. You have lots of formulas here. And here we have lots of resources on the differences between classical and quantum computing, but we explained that already. You can read all that. The differences is that classical computers are based on mathematics, quantum computers are based on physics. They're completely different. Now, a question for you, not on the slide though. What do you think the quantum computer is going to be used for? You, sir, in 10-15 years time, what do you think you're going to be using quantum computer for? You're going to have a quantum computer in 10-15 years time. What do you think you're going to be doing with it? Anybody? Idea what you're going to do with a quantum computer? Break the blockchain? Yes, you can break the blockchain.
Maybe work.
But then you end up in prison. Actually, I can teach you how to hack and not wait 10-15 years time. I can teach you if we start now, we have how many minutes? We have like less than 20 minutes. In 20 minutes, I can teach you how to hack. But you'll end up in prison, young lady. So that is why you're not hacking. There's actually ransomware. I can show you a web page that you're going to go to that web page. You pay 400 USD and they will sell you ransomware as a service. You deploy that to the University of Warsaw and then you ask them for money and they will pay you ransomware. I can teach you that in 20 minutes. You don't need to wait 20 years for a quantum computer to hack, but there are legal consequences. I can take this and I can break the window, but there is legal consequences for that. I can start jumping on this table and doing many things, but I'm breaking the social norms. So what would you be using it for productively? For your school, for your work? Yeah?
Oh, not for myself personally,
Mm.
but I was gonna say one application that governments are looking at is quantum communications through entanglement, but that's a defense application, not something I want to do.
Yes, that's a very good question, and I hope this question will help me clarify something for you people. Quantum communication is based on quantum. Quantum is physics. We're talking here about post-quantum, that's mathematics. Quantum communication test beds already exist in Abu Dhabi. There's loads of quantum communication test beds. Those are based on the actual quantum work, the physics, how the qubits communicate. It's not practical in today's terms to do that. That might take a long time. What you're worried about today is somebody securing your files, breaking them in the future. What we're going to have in the future, we don't know. But we know that we're going to have as a bare minimum this digital calculator who will break the current encryption methods. Why? Because every country, including we say US and UK, we're very nice, we don't break anywhere. That's exactly what cryptographers are working on. How do you develop? So Peter Shor, why did he build that algorithm to prove that you can break RSA? Love Grover, what did he build? He built a method that you can derail. So answer to this question is, well, yeah, did you have?
Can it be implemented somehow to the road to the AGI maybe? In that
Artificial generative intelligence, yes. So the short answer to that is you don't need a quantum computer to use on your laptop. You're not going to be using quantum computer to watch YouTube videos. Quantum computers are very good at processing very big data at speed. So where is that going to be? In big data centers. So your devices will be processing data much faster, but that for you, it's not going to be noticeable. It's going to be noticeable for the cloud service provider, Amazon Web Services, Google, because you can feed loads of data, it will process it in the blink of an eye. You will get the results much quicker. Let's say you feed all the data from all the hospitals in the world, and you ask this to calculate something. Remember, calculate something. Quantum computer won't be as smart as artificial generative intelligence. Quantum computer will just be processing data. That's all. That's the limit of a quantum computer. It will break numbers, it will decrypt, it will process data. That's going to be in the cloud computer. You're not going to be using it in your everyday life. It's going to be used for science, it's going to be used for security, it's going to be used for various other reasons. Now, cryptography at risk, what breaks and what survives. Now let's look at first at the cloud, the word cloud that you had. Oh my God. Oh my God. Personal data. What have we been talking here for an hour?
But it was sensitive and commercial data. The commercial and secret data is something that will have value, right?
Yeah. This is wrong. You all guys got it wrong. I've been talking here for an hour and I don't know who you've been eating bananas. This is not the case. For your person, nobody cares about your personal data. Really, this is going to be implemented on a national level, stealing top secrets. This is going to be implemented on financial centers, stealing the money from the bank. Has nothing to do with your personal data. I know that European Union GDPR is very much focused on personal data. Those regulations are developed based on what people think. So people are very concerned about their personal data. Do you think a hacking group in China cares about your personal data? Let me demonstrate this differently. Let me demonstrate this. Because you have to understand that this is wrong. Nobody's going to build a quantum computer to steal your personal data. I can steal your personal data without a quantum computer. Actually, let me play you a... Can you see it? Can you see it? Okay. somehow, just when I was sitting here, as I anticipated that you will get it so wrong. So let me demonstrate this. This is
person is doing on or near their phone or computer.
this is 6 years ago.
Cybersecurity researchers, stalkerware is a
6
growing
years ago.
problem, particularly for vulnerable women. I've downloaded the software and recruited my colleague Joanne to test it.
Basically, this is a BBC reporter.
Effectively, we'll call it the perpetrator's phone. And
I'm not going to show you the whole video. I can send you the link if you want to watch it. What was happening basically is you go on the dark web and you pay £170 for subscription. They give you a link, login, username and password. No technical knowledge. You could be studying, I don't know, social media studies. You might not know how to do anything with computing. You pay £170. It's called spouseware because your boyfriend will try to spy on you. Men are more jealous than women for some reason, so that's why they call it spouseware. But you know, could you use it in reverse? So he paid the subscription and he gave the phone to the young lady, his BBC colleague. So now she's watching where he's going. This is her watching his camera. His phone is switched off. His phone camera is not showing anything. She's watching that when he's unlocking his bike. She's listening, she's watching, it doesn't show anything, black screen, as if it's locked. And she can see everything.
I can see where Joe's moving. It's not just updating every so often, it's a live
Anyways, you get the
image.
point. You don't need a quantum computer to steal your personal data.
It's,
So, I can, you just send me an email on LinkedIn and I will send you this link so you can watch it. This is 6 years ago. 6 years ago. Every time you get a software update on your phone, what do you think? Do you think that software update, oh my god, that did? How doesn't it drive you crazy? When you get a software update on your phone and it says you have to update your software, what do you think? Apple is now trying to get me and slow down my computer, or do you think Apple is installing a very valid patch to a vulnerability that has been exploited? Most people are still thinking that Apple is trying to slow down their phone. They did that once, they paid a penalty, they replaced the batteries for free to so many people, they learned the lesson. When you're getting an update, it's basically, this was a vulnerability and exploit. We detected it, we developed a patch, and we sent an update. What do you think is the average time for a patch from the vulnerability being detected? It's a vulnerability in your phone. You detect a vulnerability, you detect that it's exploitable, you develop a patch. The timeline from that patch being installed on everybody's device was 300 days. That means that the hackers had 300 days to exploit this vulnerability because people were skeptical and not installing the update on their phone. So that is what you need to be really worried about if you're worried about your personal data. You need to learn how to have multi-factor authentication, because if somebody steals your password, but you have a multi-factor authentication, they won't be able to get into your social media. You need to learn that's a different course that I teach AI malware. And social engineering, for example, it's very different. Malware refers to the software component of hacking. Social engineering refers to, we have some prisoners in the UK, they're locked up because if you give them a phone, with a phone in 40 minutes they can make $1 million. They will make phone calls, they know how to scare people. So they will make very scary conversations that you would transfer the money back to them. You get a message on your social media saying, your password has been compromised. You know, take urgent action, panic. You know, you start worrying, and they say, click here to change your password. You click there, and you start typing your password. That's all keylogger is being looked on a different screen. The hacker is actually observing that. Hello, yeah, come in. So the hacker is observing, typing your password. Then the multi-factor authentication kicks in. So, you know, as soon as that is asked on the hacker phone, he's sending you the message back saying, confirm your multi-factor authentication. You send that code, boom, you've been hacked. If you're worried about your personal data, you need to understand how social engineering works. You need to have multi-factor authentication. You need to install your updates. Quantum computing has nothing to do with your personal data. It's with data that has value in 5, 10, 15 years' time. So,
Professor,
yeah?
Can I just add,
Since
I'm one of the persons who type personal data, I would just like to give the explanation short. I thought that because the question was what would cause the greatest legal damage, and my reasoning was if there is a breach of many people's personal data from a bank, that would cause a huge legal damage because there will be many people legally enforcing claims towards the banks or the national government institutions because their data was leaked. And if I read about the article that there was a breach, if there would be a breach in, let's say, some government institution that runs the health data from the patients, if that's leaked, then I guess there will be 1 million people suing the government for that. That would be a huge legal damage. If there is just the relation between the hackers and the bank, that could maybe not cause the legal damage at all. If the bank cannot trace the hackers, and that would not bring up the amount of legal work
Okay.
comparing to the personal data.
I understand your argument, and the whole purpose of this session is to change your mindset. I do understand that everybody here is worried about their personal data, not just one individual, but everybody. I understand that the whole European Union is very worried about their personal data. China is taking a very different approach. WeChat and the approach in China is very opposing to what you have over here. I'm not trying to challenge your opinion about personal data. What I'm saying is put that in a box, leave it by the door. You're gonna pick it up on your way out. For the purpose of this session, try to open your mind, because if you focus on what you already know, you're not going to learn. This was explained in this slide. So that slide actually explained it before I asked you the question. Now, let me show you something else. And because, as I said, when I work on this, I work with people that they are paid a lot more money than me, and I have to demonstrate in order to convince them. But what that means is that when you spot something that's problematic, you have to address it. But that means that you have less time to cover so many different topics. So we have like 10 minutes left, and this Malpedia is not working. What happens here in this room is that Eduroam connects and disconnects. So I'm gonna wait for this to open, because I'm trying to show you where the hackers are trying to get the most money from. And remember, it has to have financial value. Once this opens, a few seconds time, I'll come back to this. Remind me Malpedia, tell me Malpedia. So, because there's so many other things that I need to cover. So we're gonna come back to Malpedia. But let's look at some of these slides quickly. Cryptography at risk. What survives, what breaks? The three, yeah.
The only thing is, I think we finish at 12:15.
Yes, we have 25 minutes.
Oh, excellent. We have a little bit more time. Let's check if Malpedia has opened. What is Malpedia? Did I show you on the first session Malpedia? Did you guys see Malpedia? No, I didn't explain Malpedia. Okay, Malpedia is a very interesting webpage. It's the very first webpage that I found useful that has been developed by European entity in Frankfurt. So this is a German, I guess. So that's why I'm promoting it. There's loads of similar web pages that have been developed since 1990s in the US. Nobody in Europe has been developing something similar. So the reason why I'm pushing it, because I'm in the European Union state, and this is a European web page. So, but to criticize, clearly I'm promoting it, but this is not a very useful web page as you see it like this. Why would I start with this? The actual usefulness is here. Inventory. When you click in the inventory, you have library of attacks, you have families of attacks, and you have actors. So let's look at just the actors. This is the Lazarus group, is the North Korean hacking group. Lazarus is a Greek name, but actually this is a group from North Korea. This is the most prolific advanced persistent threats. So if you look at this list here, you see APT28, that's from Russia. APT1, that's from China. APT41, China. APT29, that's Russian. Lazarus group is advanced persistent threat, so it should be APT, but because it's so well known, we call it by name, Lazarus group. We kind of give it the glory about what they're capable of. They're extremely capable individuals. They don't have a quantum computer. The entire nuclear program in North Korea is being funded by one branch of Lazarus group. One branch of Lazarus group. Lazarus group has many branches. And one branch of Lazarus group has been able to fund the entire North Korean nuclear program. They didn't steal your personal data. They didn't even try to steal your personal data. They cannot get the money from your personal data. What do they work on? Let's look. And by the way, here you have the number of attacks, coverage. Here, if you click on this, you have associated families. So we said one branch of this is funding the whole. And here you would have different types of references, what kind of attacks they have. It's going to be a long grade. That's going to be I can do a whole year course on Lazarus Group alone. That's how good they are. They work on ransomware. Basically, they hack national critical infrastructure like hospitals. Hospital is a very good target. If I'm hacking something, I would go for a hospital. Because hospitals, they have limited budgets. Healthcare, it's expense. Google, you cannot hack Google. Google is making lots of money. So they have lots of money to invest in it. Healthcare is expense to the national government budget. They operate on very old computers, like Windows devices from 1998. I don't know what they operate, but they don't have money to update their systems. And that makes them a very vulnerable, very easy target. What's going to happen if you hack the hospital? People will die. So you hack the hospital, you encrypt their servers, you send a message to the government and say, hey, you're either going to pay me 3.5 million today, or by tomorrow, 100 people will die, and I'm going to make this public. Do you trust me that I can make it public? Should I demonstrate that I can make this public? Should I start publishing the data from the patients to demonstrate to the public? You're going to lose the next election. What do you think the government is going to do? They're going to pay. What is the success rate for ransomware if it's 3.5 million and above? I'm going to show you the hacking reports. They say 85% success rate. So 85% of the organizations that they hacked by ransomware, they pay the money. You never hear about that. You know, like, why? Because you're going to lose the trust in your national government to protect you. And you're going to start thinking about personal data. They're not going after your personal data. They have never hacked a group like Facebook. Actually, Google is preventing billions of attacks per second. So that's how good Google is. If I'm hacking, am I going to go after Google? I know that it's going to be very difficult to break into Google. I'm going to go into national critical infrastructure, energy grid. Well, even energy makes money. So you pay for your electricity. That means that they have money. National critical infrastructure, that's the most vulnerable. It's the services that they don't pay. Pension system, pensioners, those are taking money from the government. That means we're trying to cut down on all the expenses because we don't have money, and that's where you hit. So yeah.
I have one digression because I work in judiciary primarily, and in the last few months we had a few hacker attacks in Serbia on SEPs, and our programs were blocked, and so then they disabled all access to the computers for employees. So even we can't even USB flash, we couldn't put it in the computers because everything was disabled just because of those external attacks.
Yeah, I mean, why did they call WannaCry attack? Because once you get hacked, you want to cry. You just get a red screen. I have a copy of the screen in somewhere on my slides. It says pay us the money, or you're not going to be able to get this data like ever. So anyways, we're going back to the slides. Cryptography at risk. What is, question?
Then it means that like paying the ransom is cheaper, right, than introducing like strong security systems. Like it must be beneficial in some way for the government, right? Like if they're not changing.
Not cheaper, young lady, not cheaper. They're not operating on that mindset. Governments will suffer the cost. Governments will pay. It's not about the money. It's about people dying. They hit you in a point that you have to pay. And you imagine we sit in this room and we think, okay, we're going to hit them with an attack. It's going to cost them 3.5 million to pay or 10 million to rectify. What are they going to do? They're going to spend 10 million to rectify. They're not going to pay the 3.5 million. You hit them on the hospital where people will start dying. And then once you get the protest from all those families to say, you should have paid 3 million pounds because my father would have been alive. That's what the government is afraid of. It's not about money.
Yeah, but then, like, why don't they just implement stronger security?
On the National Health Service?
Yeah, because like then they have to pay the ransom.
Yeah, when you watch the news media tomorrow about the budget, you're going to look at this pie chart, and they're going to say 40% of all the money goes to the National Health Service, 40% goes to the pension system, the budget is left with 20% to pay for the salaries for all the admin. How do we cut the National Health Service? That's how they cut the National Service. The health service is an expenditure to the government budget. Most of the money goes to social services, social healthcare payment, pension, national healthcare. So they don't have the money to protect themselves. I mean, Google has money, Facebook has money, Microsoft has money. They have loads of profits. You hit where the government has to pay you. They have focus groups. It's a job. To be a hacker is a job. That's how they make money. An advanced persistent threat, when you talk about these groups, those are not some fat, obese hacker who sits in the basement of his grandmother and hacks into the National Health Service. No. Those are people with suits that they go and show up in the office and they get paychecks. They pay their rent. That's why it's advanced persistent threat. It's advanced, they have skills, they have careers, they have jobs, and it's persistent. Now,
So,
yeah?
when you see that quantum computing,
Yeah.
computer can break cryptography, you mean asymmetric and symmetric encryption, or hashing also?
All of it. So here we have what is at risk in this slide: symmetric cryptography and hashing cryptography. So with here it says with security margin reduction, the hashing, symmetric with key length adjustment. So all of those are at risk. Now here you have a second, rank the following cryptographic primitives. So if you can use Slido for that, this is going to be the next question, and it's going to give you cryptographic primitives by urgency of replacement under a quantum threat model. You don't really have to get it wrong, right or wrong. Is it symmetric? Is it hash? You can just play with that, and I'll continue with the slides. So here on this slide I'm introducing the NIST post-quantum cryptography. We already spoke in length about the NIST post-quantum cryptography. You're gonna get this video, young lady, so you will get the video link. It's important. When I was a student, I used to take notes, then you put them in the cupboard and you never read them. That's why I recorded. You will get the link, you don't have to take notes. Everything will be recorded and shared with you. NIST post-quantum cryptography, we already spoke about that. So let's move on to the next slide. Crystalis family is the core NIST standard. Now if I zoom in, usually I make the images into links. So let's see if this is, but you have to go into this mode. Yeah, there are links. You can't see them on your screen, but on my screen it's showing. So now I'm gonna escape, and I'm gonna go here. I'm gonna close Peter Shore. I'm gonna close this, and this it's one of the algorithms that has been adopted by NIST. Oh my God, why is it doing that now? Okay. So at the end of this session, you need to know the names of the algorithms that have been adopted for post-quantum cryptography. Another thing that I need to convince you that this is not US-based effort, US trying to open backdoors to hackers. Christos, it's one of those algorithms. Now here, if you scroll down in this link, you would find the entire description of what it does and how it does. I'm trying to find the actual paper. I'm trying to find the paper that publishes this. And this is the paper. Look at these names. The same names will appear for every other algorithm. That's what I'm saying, that there is only a limited number of people. And if you type down these names, you would find that they are associated to University of Vienna, University of Zurich, University of ETH. They're actually based in European universities. So they competed and they got this accepted. So that's the first one. Let's see if the second one, resources, NIST. I think on the second one it will actually have the association. Yes, there we are. So we're gonna look at this one more. University of Florida, second, University of Netherlands, third one, Germany, US, Switzerland, Germany, Switzerland, France. These algorithms are developed in European Union universities, and then these people have been submitting them for the competition, and the US has adopted them out of 60 different algorithms. It took a long time to argue with the European Union to say, you don't have the capacity to repeat this for another 10 years. You should have started back in 2016 when NIST started, and then you could have run these sessions in parallel. Now, if you start again, you have to call all the European organizations, Microsoft, whoever they are, and ask them if they can implement what algorithm is easiest for them to implement. Eventually, the European Union accepted the argument, and now NIST standards are officially standards in the European Union. You don't have to create this argument anymore. If you get any skepticism or doubt, remember they are developed in here, they're developed in Europe. So it's not any form of conspiracy. Going back to the slides, this is the slides of the new algorithms. I'm gonna have to click on them to open them, and then I'm gonna zoom out. Okay, so we have seen Crystallis, we have seen the lithium. This is another one. This is another algorithm. Look at this name, Daniel Bernstein. I'm gonna focus on that name. So Daniel Bernstein, mathematician, computer scientist. He's a character. I'm not going to be able to show you all the cryptographers. Actually, I can find the faces and the names of the Lazarus group, the world leading hackers. I can, but I don't have time in one session to show you all that, and it doesn't really matter. But what it matters is that the world becomes very small the more specialized you become. This person, Bernstein, he sued the United States. So he's German American, and in his lifetime, we were not allowed to talk about cryptography. I wasn't going to be allowed to come from the UK and talk about cryptography here in Poland because it was considered national secret. He sued the United States and he won, so he was able to go back to Germany and teach cryptography. He is the creator of Cha-Cha. He has multiple algorithms, but now he is the co-author, so he created Salsa 20. You can imagine, in his student days, he was probably dancing salsa and cha-cha, and that's why he named his algorithm Salsa and Cha-Cha. But he is one of very few people in the world that actually understands cryptography. He worked on the old versions of cryptography, he works on the new versions of cryptography. This person created the Falcon. He created the Spinach and various other algorithms. You could attend a conference presentation from him. In cryptography, he is something like a celebrity. In other aspects, you might see him on the street and nobody would know that he exists. Cryptography can be very niche subject area. So as you can see, he is one of very few. Falcon is another algorithm that is going through the selection process and being approved. We have a whole paper here to look at the Falcon. You can zoom in. This is going to be in the slides as a link. And again, this is developed. If I can zoom in, for some reason I can't zoom in. But maybe you can see here Zurich. Zurich, it's University of France, Zurich. And this is some German university. And here you can also see the associations. France, United Arab Emirates, France. Anyways, you get the point. These are not US-based algorithms. What is the implementation realities? Quite often we use RSA because it's fast. So you can send communications for a very cheap cost. It's not going to cost you a lot of money and it's going to be fast. When you have the most secure system, if it's going to be slow and expensive, it's counterproductive. So that is the implementation reality, is that you cannot have post-quantum cryptography on all your data. We covered that already. So going to the next slide. Accelerated crypto analysis. You can improve side channel attacks. Okay, so mathematically this is all covered. Model-driven attacks on cryptography. Yeah, machine learning and quantum computing. There's a whole branch now. And if you talk to the PhD students from Cambridge that they're working on this, they're very skeptical, and I belong a little bit to that category of the skepticals. Physicists say that we're not going to have a quantum computer, the hardware, the actual device, we actually have that. The hardware development is advancing at speed. We don't have the software. There's no software development for a quantum computer, and it's very difficult to develop software because you have to test it for a device that does not exist. So once we have a very competent quantum computer, only then we can start building the software, which means that the useful cases are not developed. Imagine you want to start a startup company and you want to build that on generative AI. You can do that today. You can go to Silicon Valley or San Francisco, you can start building and you can connect to all those people. You have the tools, you have the algorithms, everything is ready. For quantum computer, we're so far behind. We don't actually have the device, the hardware to build the software upon that. And now, if you think about machine learning, do you need machine learning for quantum computing? Quantum computing is processing data at speed. The only way that you need machine learning and quantum computing in combination is when you put them in the cloud. So the next session that we talk about blockchain in the afternoon is going to be about decentralization. Decentralization means more security. We're going into a very centralized world. You cannot have quantum computer in a decentralized system. It needs like a big cloud. You cannot have AI in a decentralized system. It needs the processing power. You think when you type to Siri and it does something, do you think that's happening on your device? No, that's happening in the cloud. It needs internet connectivity, otherwise it doesn't work. I worked 5 years on AI for IoT devices. IoT devices are low memory devices. So how to put AI, what a professor at MIT called it AI on a diet. As soon as they offered him a permanent position, he dropped that. He hasn't written a single algorithm. It's a dead end. And I honestly, after 5 years, I can tell it's kind of a dead end. You cannot have AI running on a low memory device. It needs to be symbolic AI, not machine learning AI. You know the difference? Who knows the difference between symbolic and machine learning? Raise your hand if you can. I'm not going to ask you, just raise your hand. I'm not going to ask you to explain it. Do you know the difference between symbolic AI and machine learning? I'm going to have to cover it in a different session, but symbolic AI is like when you watch Star Trek, 1950s, 1960s, they wanted to build AI based on the principles of mathematics, probability, physics. Machine learning is based on data. It's very different. If you have no data to feed to the machine, machine learning doesn't work. Imagine you have a new strain of virus, COVID 567, which is not based on any of the previous viruses. Machine learning, useless. Machine learning is not going to be able to help you with anything because you need to have data to feed to the machine. So what's going to happen with that previous slide? When you have a cloud device that's connected to a quantum computer and artificial intelligence, that's the perfect recipe for artificial superintelligence. At end of technological singularity, end of the world as we know it, when machines are becoming smarter. But they're not going to be connected. Cloud is going to be the connection point. AI does not require quantum, quantum does not require AI. When you need a linking technology like Oracle to put them together. Regulatory context, NIST 2 directive. This is a slide which I could have covered in a lot more detail because there's a slide, a question on this, but I won't really cover it. NIST is a directive in Europe. Now, this is on scale 1 to 5. How important will post-quantum mitigation bill be for demonstrating state of art under NIST? Let's see. Okay, so RSA, actually it's a correct answer. I'm pushing the second one, and this is just from scale 1 to 10. How critical do you think post-quantum cryptography mitigation would be to demonstrate state of the art under NIST? But since we don't really have time to cover NIST in many more details, that's going to be challenging to answer. Regulatory context of DORA, Digital Operation and Resilience. This DORA is different than DORA. I have the other DORA open here. This is the DORA Declaration for Research Access, and they're very different to the DORA on the slide. So why do you use this DORA? This DORA was developed, let's say you type my name in a search engine. So you go here and you type okay, you go to my Scholar profile and you see these H indexes here. Now what DORA was saying is that you don't really need to count things by those numbers alone, you need to look at the impact of society. So that is what DORA means. Here we're referring to the Digital Operation and Resilience Act, which is one of related to cryptographic relatives. The key question from legal perspective is, imagine that you're getting a legal case against you. Why did you choose that specific algorithm versus the other one? And what's going to happen if the European Union has already adopted the algorithms that I showed, Kyber, Spinach? if your organization is not adopting one of those, how can you legally justify in the future that your organization was secured? Because NIST has undergone 10 years of selecting those algorithms. And let's say you have an organization that picks a completely different algorithm, one of the 60 algorithms that they were in the first instance. Maybe it's more secure, but you still get hacked. I have demonstrated in these slides that you don't need quantum computer to hack an organization. That, let's say, what does cryptography mean? From my device to your device. What if I hack your device? What if I get into your device like that demo that I showed you? Then I can see everything that you're typing on the screen. I don't have to break into the network between these two devices. Is another question which you can skip. Now here on this slide, I have a structure of how you can design post-quantum mitigation strategy. Remember one thing, hybrid approach. Hybrid approach is promoted by NIST. It means that you apply post-quantum cryptography for that very small fraction of your data that's still valuable, and that means you sit with your organization in a room like this and you find out what your assets are. What is the value of your data today, and is that still going to be valuable in 5, 10, 15 years time? You need to identify that very small percentage of data that will have value in the future. Once you identify that, you need a hybrid approach. Hybrid approach means you secure that with post-quantum cryptography. You keep RSA and current cryptographic systems for everything else. You don't have to apply post-quantum cryptography for everything. It's expensive, it's time demanding, and it's just not practical. So here is a process, steps for hybrid transition. ISO has a recommendation, ISO International Standards Organization for Standardizing, and NIST has a process. So you can look at those two maps and pick the one that is most relevant for you. Auditability and evidence. If we're looking for auditability and evidence, why do we always look at cybersecurity standards? We have an old office for auditing. We have actuaries. So we need to look at how do they perform auditing for other systems and apply that here. You have auditors, they are experts in auditing. We tend to think that we need computer scientists to audit some of these algorithms. If you see how difficult, and as you saw that PDF with 600 pages, how many people can audit that? So if you have 5 people in the world that actually understand the post-quantum cryptography correctly, do you think somebody else can audit that document? You need to apply backup mechanisms. Sector-specific considerations, it will be specific to financial, to legal, to healthcare. It's not going to be the same. Here I have 1 minute left for this, and this is a timeline that I have developed based on companies that are developing quantum computers. And according to IBM, let's just zoom into this. And why is it not? Exit. Yes, there we are. According to IBM, by the end of 2026, we're going to have the first use case for a quantum computer. So if your timeline is showing 5, 10, 15 years time, these are the companies that they're developing this. And some of them are saying, we're not going to have a full quantum computer, but as of this year, 2026, we're going to have some use cases from a quantum computer. Remember, they do have quantum computers already, just that they're not powerful enough. And if you look at this timeline here at the bottom, even the worst case scenario, which is from expert surveys, it's 2040, 2030, 2040. Now, how much time do we have? It's exactly the end. Do we have, let's say, 2 minutes?
I mean, it's up to you.
Okay, let's do a quiz. Quiz, guys. Quiz. Log into Slido, let's do a quiz. Each question will come up and very quickly it will disappear. So on this quiz here, let me push the quiz. Go to question. Are you seeing this as a question? Let me see. No, why are you not seeing this as a question?
You can put present on the,
Yeah. Oh, scale of 1 to 10. Why I don't know how to use Slido? So I need to Correct answer not selected. Okay, maybe I can go back to lead anyways. Go back to the second one. You see what's the trick here? It's actually telling you the questions. Go to the question. I'm gonna have to work on this quiz, guys, because it's not. Yes, do you know how to use Slido?
Yeah.
I created a quiz, but now it's saying
Slido with the students. Yes.
This is quiz, right?
Yeah.
Oh, you cannot run it because you have not chosen the correct answer. So you.
That needs to be deleted.
Okay.
I need to delete that. It's untitled. 0 votes. Here. Yeah. And here. Delete those with no answers. Because we have more questions.
This one too deleted?
Here maybe? Delete question.
Okay, and now.
Yeah. Tech support. So you need to join the quiz, please. You don't have to use your real name. Do this as a practice in cybersecurity. Choose a name. Unicorn 1235. Blueberry. Black Betty. Put a fake. Sorry? Satoshi Nakamoto. Yes, you can be Satoshi Nakamoto. Okay. So we're waiting more people to add. We have 15 people already joined in, 16. I'm just gonna wait until 20 people join in and then I'm gonna, we're doing a quiz if you want to join in the quiz. 16, 17, 18, 19, 20, okay. So, join the quiz now. First question, okay? Which quantum algorithm, you have 17 seconds, which quantum algorithm directly breaks RSA elliptical curve? It's a trick question because we discussed 2 of those, but we didn't really have enough time to cover which one directly breaks RSA elliptic curve. So it's going to be our guess. Grover algorithm. Okay, so let's open the questions and answers. Desktop also. Slides. Quiz. B. Yes, B. So B for that one.
Peter Shaw.
Yeah, Peter Shaw. Then. Okay, it reveals the answer. Okay, yes, okay, I see it. So how do I go down to the next question?
Let me help.
Yeah.
I think you can
Just keep the screen with the questions.
I clicked something. Yes, it worked.
And after the question is running. After they finish, they choose the answer. You just click next here.
Aha. Yes. So which least standardized algorithm replaces RSA for key? And now.
just
Next, click next.
yeah.
This
shows the right answer. Yeah.
Kyber. One word about this Kyber. They're changing the names. So MLChem is actually they can standardize the names. In the future, when you look at post-quantum cryptography, it's going to be MLChem, Chem something. It's not going to be spinach, the lithium. I call them Kyber because that's the original name. They will change the name to be standardized. It's all going to be the same name, just one letter difference in between. Why a hybrid cryptography legally attractive during post-quantum cryptography transition? We did find time to cover this extensively. Why is it legally attractive? You have 7 seconds left. Okay, so this is the answers that we got. Hedges against premature standard failure. Which regulatory framework explicitly links cryptography to management liability? 7 seconds left. We only discuss one framework out of those on the actual slides. So NIST 2 is the only framework that appeared. GDPR, we discussed it, but it was not in the slides, and we discussed it in the context of privacy. NIST 2 was the only framework. I think this is the end, the last question. So A is the first score, got 3 out of 5. Uni is the second, Cherry third, Petar is the fourth, and Blueberry is on the 5th place. This is the end of the session, and I'll see you in the next session. Have a good lunch break.
So guys, we'll start at 13:30 and enjoy your lunch break. I mean, we can lock in the room if you prefer that. Yeah, we can do that.
Is it yours?
It's mine.
Is there a canteen somewhere here? Canteen for food?
I think it might be closed on the weekend, but there, just outside of the main gate, there are several places. Depends what food you like.
I want coffee.
Coffee. So right out of the gate left, there's 2 coffee places. One is Green Narrow Coffee Place. And it's good. I recommend it. A little further is Costa Coffee.
Okay.
Hello, hello. Yeah.
You're a PhD student. Let me switch off the camera.